Solar Eclipse Wrap-Up. This presentation was done for the North Shore Amateur Radio Club. This is a picture of the solar eclipse, which was taken from Stan KM4HQ in the States at the totality point of the solar eclipse. Beautiful picture, and we have some stories to tell too, though. So, going back to the day of August 21st, 2017, the solar eclipse conditions were fabulous. We had clear sky, not a cloud in the sky, and the air pressure was 1023 millibars, which is a beautiful day, and temperature 27 degrees Celsius. The solar flux was rising, was 90 and was rising. And this was quite unusual because the solar cycle is in decline, and a couple of months earlier the solar flux was almost at 70, and only in the last 2 weeks before the solar eclipse the solar flux rose quite rapidly, and it made up for some spectacular sunspots, which will have a severe impact on how we measure this propagation change of the moon. So now going back to the solar weather. The solar weather was active and turbulent despite of what everybody was hoping. And so we just had a solar flare had released a couple of days earlier, and the D layer was activated. The D layer is a layer that attenuates the lower bands, and the more activated it gets, the higher the frequency of this attenuation gets. And at the same time, NOAA was forecasting a G2 magnetic storm. The eclipse totality for North Vancouver was 85%. This is the solar measurement from ON1 DHT, and this was during the solar eclipse in 1999 on Belgium, and the measurement shows that the signal, that incoming signal, as long as the sun, before the sun gets covered by the moon, the signal is there, and it drops quite rapidly off. And then when the moon releases the sun again, it shows the increase of the signal. And that's basically what we're trying to measure. The RF-Seismograph is very similar in design for this process. The only difference is that we made it a scanning RF-Seismograph, which allows to look at 6 channels at one time. So you can look at 6 bands and how the propagation changes. Here is the RF-Seismograph multiple station measurement topology, and it's basically covering all of the lower mainland. I could basically go around the world using the internet, and every station is independent, and it's not reliant on any other station. Like once it's set up, the test measurement is and the real-time graphs are uploaded as graphics to our FTP server, and can then be distributed through the internet. And there was also a possibility to upload the measurement data after the measurement was over, so we could have a digital record of it. Measuring locations, we had 3 stations that we had set up for measuring. We had the MDSR test station in Lynn Valley, the mobile MDSR test station at the Cypress Cross Country Ski Area, and we also had Joe Jonkas from Newport, Oregon, WA7MHB, joining the fun, and he was the perfect location because he had totality, and he gave us a really good reference on where signals go when the sun disappears behind the moon. The main station for monitoring is the is the MDSR test station in Lynn Valley. Here you can see the antenna. It's a HG18HD Junior, and it's mounted on the roof of the 3287 Mountain Highway townhouse complex. The radio was an FT950 with CAT control for the MDSR and RF-Seismograph software. The BiLiF unit was used as an interface between computer and transceiver, as the computer was used on Asus Windows 8.1 i5 CPU. It was running the MDSR and RF-Seismograph software during the Eclipse and automatically uploading the images to the internet. Here, this is the setup for Cypress Mountain. The antenna that we used was an MFJ 1979, and it is a telescopic antenna, and it extends to 5 meters, so that is a quarter wave on 20 meters. And in order to make it resonant on 80, we actually had a coil connected to it. And the radio that was connected to the antenna was an FT817. We used CAT control for the MDSR and RF-Seismograph software again. The portable BiLiF unit was used as an interface between computer and transceiver. And as a computer, we used the Asus Laptop Windows 10, and it was running the MDSR and the RF-Seismograph software during the Eclipse. This is the station setup in Newport. This is the location, and it's just north of Newport, Oregon, and the antenna were mostly home-brewed dipoles and a Yagi for 20 meters. The radio also was an FT950, CAT control for MDSR and RF-Seismograph software, and he used the LIF 2016 unit as an interface between the computer and the transceiver. The computer was a Windows 10 machine. It was also running the MDSR and RF-Seismograph software during the Eclipse and uploading images on the web for real-time viewing. So here we show the shadow of the moon racing over the planet. And I brought up the website here. And this is a picture of the moon shadow from Sky Calculus. They had a weather balloon that they launched with a camera on it, and they were taking pictures of the lunar shadow. And the as you can see, like the lunar shadow is quite small compared to the rest of the planet, and therefore we think that the effect of the moon shadow is so limited that it can easily be overpowered by a strong solar activity. So let's just do the math here. We calculated the total area of Earth, which is 510 times the power is 510.1 times 10 to the power of 6 square kilometers, and then only half of that gets hit by solar rays, so we divide it by half. So we have 255.05 times 10 to the power of 6 square kilometers of area. And then we calculate the surface of the lunar shadow, which is 50 kilometers in radius. So square that and multiply it by pi, we get 7,854 square kilometers. So if we take the surface that receives sun and divide it by the surface of the lunar shadow, we get a ratio of 1 to 32,486. So this shows us right there that the solar shadow doesn't have a lot of impact on energy difference. Now this means global effect of the lunar shadow causes only a 3.08.10 to the power of -5 drop in energy and it's probably a bit higher because there's an ombre and the moon that we have to consider. So it's probably a bit more than that, but it's still very small. And here we have the sunspots as they appeared in September, beginning of September 2017. The rotational of the sun, which is about 25 days, would mean that when the solar eclipse happened 2 weeks earlier, these sunspots were just on the side, but they were growing rapidly and they were causing a lot of trouble. And this image was recorded in September, and this was just recorded before the before the sunspots really got active and released a whole bunch of N-class and X-class flares. So this is the solar flux measurement from NOAA. So NOAA keeps an updated solar flux progression graph in their website, which can be downloaded. This I downloaded a couple of days ago to make that presentation. And as you can see, the graph is a running total, with an average, and it takes a lot of solar change in order for it to increase. So, and you can see that the radiation of the sun definitely increased here at this point, and it increased strongly enough, and it was for a long enough time to really make an impact on that graph. And it can actually be considered kind of like an Indian summer of solar flux before we just go down into the solar minimum, which is only a couple of more years away. So here is the effects of solar flux on the D layer. So this is a flare, the N-class flare that happened on August 18th, just a couple of days before the solar eclipse, and it basically wipes out the lower band communications in North America. It's a direct hit, and you can see the area that's lit up. It's attenuated, and it goes up to 20 megahertz for attenuation. And this high solar activity continues for a month after this one happened, and it creates a very interesting situation during the solar measurement. So there's even a strong flare during the solar eclipse. So this is the measurement from the new solar flux instrument from the Dominion Radio Astronomy Observatory in Penticton. The big spike in the middle is the M-class solar flare that happened during the eclipse. And even the increase in noise before the flare is also caused by the sun. And unfortunately, at no point can we see a declining propagation effect during that happened, that the solar shadow would cover up the sun and it would actually decrease the radiation that we would see. Here we compare the two main monitoring stations. So the first one is WA7MHP, Joe Janka's station in Newport, Oregon, and he has a lot of propagation in the morning, especially on 40 meters. You can see here, and also on 80 meters. I can see there with the green graph. And over here you can see the solar eclipse, and you can actually see that the green propagation, which is 80 meters, just peters out as the sun rises, and it doesn't come back even though that we have the eclipse. And the 160 meters, like there's some propagation here, you can see, and then it just totally flattens out, and even it doesn't come back. So there's no effect of the sun that we can see. And the reason that we didn't see this is because of the D layer. The D layer was so excited that it would not allow any signals pass below a certain frequency. And the same area, as you can see the same thing here. On 80 meters, there is just nothing happening on 80 meters. You would think that as the eclipse blocks the sun, you would see the LOF go up, and you would actually go down, and you could actually see propagation happening. But unfortunately, nothing like that happened. So it's just one of those things, I guess. So this brings us to the apex of the solar unrest. So the solar activity just continues to get worse after the sunset. Then on September on September 6th, the high solar activity came to a peak with 2 X-ray flares at 12 Zulu time, and it was enormous. There was an enormous flare from the sun, and it shows up right here. And you can see that even though they released this much energy, there's still more solar flares here, and there's two more that are almost X categories. And as you can see, the solar proton flux goes up after the flares. It will take about a day or two for the solar proton flux to arrive at Earth, and then it will increase the activity that way. Geomagnetic activity is even more delayed, and you can see that right after the flare, the geomagnetic activity is low, and then it will take a day or two, and then it picks up, and it actually turned into a G4 storm, which was one of the strongest I've ever seen. So here we go again. This is a picture of the X-ray flare that actually happened, that released that strong X-class, those actually 2 X-class flares. And it was a double peaking flare with a second burst reaching into the energy level that's currently not classified. So we were lucky that this spot was actually 45 degrees away from our planet. With all my years of monitoring the sun, I cannot recall a flare that was that strong. It may be comparable to that infamous Hydro flare that we had in the 19th century. The only difference is that hydro flares are usually created by filaments and not by sunspots. But it sure was a strong flare. So here we're talking about the propagation after the X-ray flare. First of all, the X-ray flares, when they happened, North America was not sunlit, so we couldn't see the actual impact, which is kind of sad, but lucky in a way, because we didn't have any problems that way. Maybe the strong X-ray flares would have caused all kinds of problems with the sensitive equipment that is working on the whole planet that is working especially in North America. But it definitely had some effect on the 15-meter band. And unfortunately, this propagation is short-lived, because after the radiation of the X-ray flare excites the layer so you can get propagation, the proton storm hits, and it kills all the propagation. So you can see the blue here, which is 15-meter propagation, and you can see that the green and the red, the red, the purple, and all excited having propagation. and as soon as the storm hit, the propagation, of course, goes away. So this is just to show how the RF seismograph is connected to the transceiver. It's actually quite simple, just a shortwave antenna, and usually the bigger antenna you have, the better. The goes in a shortwave receiver. The NIF interface is between the option filter port and the sound card of the computer, and cat control to control the computer. And because it uses a 24-bit ADC, it can measure the background noise very accurately, and also has a very high dynamic range. This is the LIF and BiLIF hardware. So this is the LIF 2014. This is a Soho version of the unit. It's easy to build, and it doesn't take a lot of extra tools, and you can just build it with a regular soldering iron. And it's below there is the up converter unit. So the up converter unit and down converter unit need to go together, and they make up the BiLIF unit. This is the LIF 2016, which is the SMD version of the RX down converter, and it's so small that it actually fits into the option filter slot of the Yaesu radios, and you only have to provide 12 volts wired inside the radio to the unit to work. And when you activate the option filter port on the output, you get 12 kilohertz output ready for the sound card. Those are the references for this presentation. There's some really interesting things. 11 years of sporadic E. Definitely a very interesting article. NASA Solar Eclipse Experiments 1999. That was actually done by Guy Rowles. And Guy Rowles' experiment together with ON 500. That was in Belgium. Then we have the National Research Council of Canada, DRO website. The NOAA Communication Dashboard, which is a very interesting site. So if there's anything happening on the sun, usually you can find it there. Spaceweather.com is a very good site. It gives you overall view about auroras and informs you about what goes on the sun. Download the software, our software, or to participate in our project. This is our website here. If you have any questions, email me, and I want to thank you all the participations and the patience for the presentations. You can order kits online, and there's always somebody here if you get stuck with making a conversion of your radio. But we're definitely interested in having as many people monitor the background noise and propagation to see where this leads us in the future. Thank you very much.